Today in the workshop we'll be working with LIDAR. We'll take a look at two LIDAR devices. The TF Mini, which is an inexpensive LIDAR unit that you can use for collision avoidance, and the RPLIDAR, a LIDAR device capable of doing a full 360-degree sweep. There's plenty to scan today, so welcome to the workshop. Hello and welcome to the workshop. Today we're going to be working with a really cutting-edge piece of technology. And before we get started, I want to tell you a little background story behind this. Now, about 2 months ago, in response to one of my other videos, I got a comment from one of you asking if I could do a video about using LIDAR. And I responded to the comment and said I would love to work with LIDAR because I think it's a really interesting technology. The only problem is the commonly available LIDAR devices and sensors were just too expensive to be using here in the workshop. I tend to try to use components that are inexpensive because I want you to be able to reproduce the things I do as well. And if I start working with $200–300 components, no one's going to be able to afford to do that. Well, it was after having this discussion that I had another discussion with the good people over at DF Robot, and they pointed out that they have a couple of LIDAR devices that are not at all expensive, and they have actually been kind enough to send me not one, but two of these devices, and I'm really excited to be able to show you these two devices today. Now, one of these devices is a stationary LIDAR device, and it goes for the whopping price tag of $40, which is really absolutely remarkable. The other device is a full 360-degree rotating LIDAR, similar to the type of LIDAR that you have seen on top of self-driving vehicles, and this goes for an unbelievable $100. So this really brings the cost of LIDAR down to the point where we can start using them in our robotics experiments. Now, LIDAR may seem like a very new technology, and that's because we see it in self-driving cars, and that's a very new technology. But in actual fact, LIDAR has been with us for a very long time, over 50 years. LIDAR was actually developed not long after the laser was developed, and was pretty well confined to government and military experiments. The most famous use of LIDAR in the early days was during the Apollo 15 moon mission in the 1970s, when they actually used LIDAR to do a topographical map of a section of the moon. Nowadays, of course, we think of LIDAR as being used as one of the navigation systems in our self-driving cars. And so we would love to be able to use this technology within our robots, and with these inexpensive devices, now we can. So the way this episode is going to work is as follows. I'm going to do the usual, show you how LIDAR works, and explain why you would use LIDAR in certain situations. And I'm going to show you a few experiments with the two DF Robot devices that were provided to me for this video. But before we do any of that, I want to show you these two devices. So let's go take a look at them right now. So here are the two devices that DF Robot were kind enough to send along for our LIDAR experiments. The first one here is called the TF Mini LIDAR sensor, and I'll show you that one first. Now, here's the sensor itself. As you can see, it's got a source and receiver on it with a couple of lenses, and a whole bunch of circuitry, and a small connector for connecting it to the outside world. Now, in order to use that connector, they were actually kind enough to supply not one but two cables. Now, this cable has got the little mini connector on one end for the LIDAR, and another connector that you could put onto a printed circuit board in order to connect the device. This connector has the mini connector on one end, and on the other end, they've got 4 of these female DuPont connectors, and that's actually perfect for doing experiments with breadboards and that. So that's the TF Mini LIDAR. Let's put that aside over here. Now this is the RPI LIDAR, and this is an absolutely awesome little device. And it's really packaged nicely, I'll have to say that for it. Let's just open it up so I can show you. It comes with a little packet at the top here first. And in the little packet you get a cable and a little note on how to connect the LIDAR up to a PC using an adapter that's included in the box over here. Now, as you can see, this is packaged beautifully. This was sent to me from China, and it arrived in perfect condition. No surprise because of this great packaging. This is the little adapter device that can be used to connect the LIDAR directly to a computer. It's got a connector on one end for this cable, and on the other end it's got a micro USB connector to connect to your computer. And this is the device itself. Now take a look at this. Now this is a real little beauty. This is a full scanning LIDAR unit. You can see the transmitter and receiver over here, and it's on a scanning platform with a motor. It's a completely self-contained unit. Has a processor and everything on it. I've got this cable here to hook it up to the USB adapter. And there you have it. A beautiful little device, amazing quality, and amazing value. So let's go take a look at what we can do with these devices now. So what exactly is LIDAR? Well, the original meaning of LIDAR was light detection and ranging. It was based on the acronym for radar, which is radio detection and ranging. These days, LIDAR can also stand for light imaging detection and ranging, which is a more accurate description of what it does. LIDAR uses a focused beam of light and a sensor to detect the range and reflectivity of a remote object. LIDAR is used in survey applications to create high-resolution maps, and of course it's used in self-driving vehicles and robotics, which is the interest that we have in LIDAR. Basically, LIDAR works by sending a beam of focused light to a remote object. The beam is reflected back to the LIDAR sensor. The distance to the remote object is determined by the travel time of the beam, which of course is traveling at the speed of light. The reflectivity of the object is determined by the beam's intensity. In surveillance applications, LIDAR is often carried in an aircraft, which beams the LIDAR light beams down toward the Earth, which are reflected back to the aircraft. Here's a NASA-provided computer animation of a LIDAR scan of the Amazon rainforest. Now, in self-driving vehicles, LIDAR is used as one of the primary sensors. It's used along with an orientation sensor that determines where the vehicle actually is at the moment, as well as a very high-powered computer and software to correlate all the information. In actual fact, self-driving vehicles use several LIDAR sensors, as well as radar, camera, and other sensors to determine their position and the position of objects around them. Here's an example of the type of data that a LIDAR scan on a self-driving vehicle would be using in order to determine its position and the position of items around it. So now let's get started with LIDAR. So let's compare the TF Mini LIDAR sensor to a couple of other methods of sensing distance and proximity. Now I've got two other devices other than the TF Mini over here to show you. This one I'm sure you're familiar with. This is the HCSR04 ultrasonic sensor, and it's got a source and a receiver that sends out ultrasonic signals in order to measure distance. Now we did an article and a video about the HCSR04. The HCSR04 has a minimum range of around 2 centimeters and a maximum range of about 4 meters, and it's accurate to within about a half a centimeter or so within that range. So this is pretty good for detecting objects in the distance that you would normally encounter in robotics. Now, it uses ultrasonic sound, and it doesn't work very well outdoors. It works a lot better indoors. It can be interfered by other sound sources, and some objects tend to absorb sound as opposed to reflect them. So this is good for certain objects, but in other applications it's not so good. Now, this is an optical source sensor arrangement that is actually used as a proximity detector, and it's got a little potentiometer on it over here, a little trim pot. Now, the way this device works is it sends out a beam of infrared light and looks for the reflected beam coming back. But instead of using it to measure distance, it simply sends it as a trigger, so the output pin over here will go high when an object is detected within the detection distance. You set the detection distance by using this potentiometer. So this is not very good at all for actually doing distance measurements, but is great for finding out if there is a device immediately in front of you. This only has a range of about a meter at the maximum, but what you would use these for in a robot is you'd strategically locate a few of these on the robot, and you would use this pulse over here to drive an interrupt on your Arduino or Raspberry Pi or other microcontroller, so that if the robot came in proximity to something, this would go high and you would be alerted to it and then could take the appropriate action like stopping or moving the robot. And here, of course, we have the TF Mini LIDAR sensor. Now, this has a minimum range of about 30 centimeters, so it's not very good for anything closer than that. However, it has a maximum range of about 12 meters, and that's a really long distance, so this will cover any situation that we have indoors and a lot of outdoor situations as well. This is also much better at working outdoors than a device like this would be. Now, of course, this is much more expensive than these two devices, so it's really a trade-off between performance and capabilities. And in many designs, you would use all three of the devices. But I just wanted to show you what the difference is between the different types of proximity sensors that you can use in robotics. The TF Mini LIDAR is a low-cost stationary LIDAR device. Instead of using a laser beam, it uses a focused infrared LED, and this keeps the cost of the device low. The range of the TF Mini is from 30 centimeters to 12 meters, which is approximately 1 to 40 feet. The device has its own internal processor and communicates with external devices via a serial input-output port. It has a maximum sample rate of 100 Hertz. In other words, it can take 100 readings every second. And those readings will have an accuracy of 5 millimeters, or half a centimeter, over its entire range. The TF Mini has a 4-pin connector on it. Here is the pinout of the TF Mini. Now let's take a look at those pins in detail. GND is obviously the ground pin. VCC is the supply voltage. The device requires 4.5 to 6 volts to work, so it'll work well in a 5-volt power supply. TXD is the transmit data line. Note that this is a 3.3 volt logic line and not a 5 volt logic line. RXD is the receive data line. It is also a 3.3 volt logic line. Now let's take a look at how we use the TF Mini LIDAR. Now, as you just saw, the TF Mini makes use of 3.3 volt logic levels instead of the 5 volt logics that most of us are used to working with. Now, we've worked with 3.3 volt logic before. If you remember when we did the motion sensor video and article, it's a 3.3 volt device, and we fed it directly into a 5 volt Arduino without any problems. So here's how interfacing 3.3 volt logic to 5 volt logic works. When you have a 3.3 volt output, you can safely put it into a 5 volt input. Obviously, it's not going to exceed the voltage. It can only get the 3.3 volts, but it will also work correctly. And the reason for that is that TTL logic, which is what we call the 5 volt logic, TTL meaning transistor logic, 5 volt logic actually has a threshold of 2.8 volts. So in other words, any signal over 2.8 volts will be considered a digital 1. Anything below 2.8 volts is going to be considered a digital 0. And so since 3.3 volt logic satisfies that requirement, you can safely feed the transmit output of the TF Mini into an input on your Arduino without any problems. Going the other direction, however, is another story. Feeding a 5 volt output from the Arduino into the 3.3 volt input on the TF Mini can be very dangerous. Now, the inputs can be tolerant to some degree to the 5 volts, but it's not always safe to assume that. So you'll need to do something to drop that voltage. Now, one way of doing that is just with a couple of dropping resistors, but calculating the values can be a bit tricky because it really depends on the individual situation. The best way of doing this is with something called a logic level converter. Now, these are very inexpensive devices, and they're available as 1-channel, 2-channel, 4-channel, 8-channel converters, and they basically just take a 3.3 volt signal on one end and output a 5 volt signal on the other end, or the reverse. They take a 5 volt signal on one end and output a 3.3 on the other end. Most of these devices are bidirectional, so it doesn't matter whether you connect them to inputs or outputs. They will work as long as you keep all the 3.3 volt logic on one side and the 5 volt logic on the other side. Now, on the breadboard I'm about to show you, I've got a voltage converter right here. I don't know if you can see it. It's this small little item here. This is just a 2-channel voltage converter. Basically, it has inputs and outputs for the 2 channels, plus a ground connection, a 5 volt, and a 3.3 volt connection. Now, this 2-channel converter is a very handy thing to have around your workshop, and they're very inexpensive. You can pick these things up on eBay, and I suggest that you pick up a handful of them because you're going to find a lot of uses for them. I like the 2-channel ones because they're very good for I2C buses, and quite often with the I2C bus, you have a situation where you have a 5 volt device and a 3.3 volt device, such as an Arduino and a Raspberry Pi, and you want to tie them together. Again, it can be done with resistors, but the safest way of doing it by far is with a logic level converter. So now that we've discussed this important aspect, let's take a look at how we wire up our TF Mini to our 5 volt Arduino Uno. So let's hook our TF Mini up to an Arduino Uno. We will of course need the Arduino Uno and the TF Mini, as well as a logic converter to convert the 3.3 volt logic signals on the TF Mini to the 5 volt signals required by the Arduino Uno. We will begin by connecting the 5 volts in the Arduino to the VCC connection on the TF Mini. We'll also connect 5 volts to the V-in connection on the logic converter. This is the 5 volt power supply input for the converter. We'll take the ground from the Arduino and connect it to the ground of the TF Mini. We'll also connect it to one or both of the ground connections on the logic converter. In actual fact, these are internally connected, so you really only need to connect one. The 3.3 volt output from the Arduino is connected to the 3V3 input, or the 3.3 volt input, on the logic converter. Next, we will connect pin 10 from the Arduino to one side of the 5 volt logic converter outputs. I'm using 5A. The corresponding 3A, which is the 3.3 volt side of that, is connected to the TXD connection on the TF Mini. In a similar fashion, pin 11 of the Arduino is connected to the 5 volt 5B connection on the logic converter. The corresponding 3B connection is connected to the RXD connection on the TF Mini. This chart will show you the wiring and make it simple to follow. So now that we've wired it up, let's take a look at a sketch we can use to test this out. Now, before you run this sketch to control the TF Mini, you're going to need to install a new library into your Arduino IDE. So open up the IDE, and go into Sketch, and go into Include Library, and go to Manage Libraries. Once your library manager opens, go into the filter box and type in TF Mini. There'll be one library in the result, and that is the one you wish to install. When you click the More Info button, you will get an Install button over here. My library, as you can see, is already installed. Once you've installed your library, just close the Library Manager. Now go into File, go into Examples, and scroll down until you get to the Examples from Custom Libraries. Under TF Mini, you will see one example called Basic Reading. This is the code we're going to be using, so select that and open it up. And I've done that over here. Now it starts off with a number of comments, lets you know which two pins we've connected the TF Mini to, because we're going to set up a software serial port on those pins. The Arduino Uno, like many models of Arduino, only has one serial port, and those are on pins 1 and 2. We would like to use a second serial port to connect the TF Mini and use the original serial port for our serial monitor. In order to use a software serial port, we include the software serial library, which is part of the Arduino IDE. We will also, of course, include our TF Mini library. We'll then set up the software serial library for pins number 10 and 11. These are the two pins that we will be using to connect our TF Mini. We'll also set up an object called TF Mini using the TF Mini library. In the setup, we initialize our serial port. This is the one that we are going to be using our serial monitor on. Notice the speed that we're initializing it at. Many of you run the serial port at 9600 baud. You're going to need to bump up the speed because the data is coming at us pretty fast. We also then initialize the software serial port. And we initialize the TF Mini and assign it to that software serial port. Now the loop is very, very simple. We take two unsigned integers, 16-bit integers, and we define them as the distance and the strength. And the distance is the TF Mini object's getDistance property, and the strength is the TF Mini object's getRecent signal strength property. Then we simply display these on our serial display. We give it a short time delay and do the loop over and over again. So now that we've seen the code, let's take a look at it in action. Okay, I've got our little TF Mini demo hooked up, and you can see the serial monitor right now. It's reading a straight 126 centimeters, which I'm sure I'm going to find is the distance between the sensor and my ceiling. And I'll pick this up and just kind of move it around the room a little bit. And as you can see, we get various readings as we go around the room. Now, one thing I want you to notice is I'm going to aim this back down at the table. You'll notice I'm just inches from the table. Here, I'll do this against the wall if you can't see that. Note that I'm getting a reading of 30 centimeters, which is obviously incorrect. That's because 30 centimeters is the minimum amount that you can read with this sensor. But one thing about the sensor is it's very directional, much more directional than an ultrasonic sensor, and the data comes in very fast. Remember, you can get 100 readings per second from the TF Mini. So as you can see, this sensor is very accurate, it's very quick, and would make an excellent sensor for a collision-avoiding robot. The ultrasonic sensors work well for this too, but because you can't take as many readings per second, it's always possible that an object could move in front of your robot in between readings. With something that takes 100 readings a second, that's far less likely. So now that we've seen the TF Mini, let's move on to the RPLIDAR device. The RPLIDAR is a 360-degree omnidirectional LIDAR scanner. It uses the principle of laser triangulation to determine distance. The unit can sample up to 8,000 points per second at 10 Hz. The 10 Hz refers to the rotation speed, so that would be 10 rotations per second. It has an internal wireless connection, so it doesn't use slip rings to connect to the rotating section. It has a range of 12 meters, which is approximately 40 feet. The RPLIDAR has a 7-pin connector. Here are the connections on the pins. Notice that there are 2 ground connections. Let's look at those connections in detail. The GND connections are obviously the grounds. RXD is the receive data. TXD is the transmit data. These are 5-volt TTL level. VCC is the 5-volt DC logic supply for the device. Moto CTL is the motor control input. This is a pulse width modulation input to control the speed of the motor. And VMoto is the power supply for the motor, which also requires 5 volts DC. Now the scan rate of the RPLIDAR is controlled by the motor speed, which in turn is controlled by PWM. The sample rate, on the other hand, is determined by the controlling software. These rates can determine the scan speed and the accuracy of the device. Here are some example scans at different rates and sample rates. Note the difference between the scans in terms of speed and the number of points retrieved. So now let's start using the RPLIDAR for ourselves. Now you may recall when I unpacked the RPLIDAR device, there was a couple of accessories included. There was a little USB adapter, a cable that connected the USB adapter to the RPLIDAR, and a little card that gave you some information. On the little card you will find a link, and I've got the link repeated in the article associated with this video. And this is to download some software for it, a software development kit and some sample applications. And so I want to take a look at that right now. Now the software development kit and the applications are actually available for all 3 platforms, meaning Linux, Windows, and Macintosh. However, there is one application that is only available for Windows, and it's actually the one that I think is the most impressive. So for that reason, I've brought a computer into the workshop. I've got 2 computers in the workshop already, but they're both Linux. So this is a Windows notebook that I'm going to be using for this demonstration. Now I've got my RPLIDAR mounted over here on this little jig just to give it some space. And I've got the serial device connected to it, and I'm going to connect this via USB to my serial port on the computer. Now when I first connect this up, you're going to notice that the RPLIDAR just spins continuously. That's because it's not being controlled, so it's just getting power to the motor, and it'll just keep going and going. Let's take a look at what's in the SDK right now. Now, when you open it up, you'll see 2 different directories, SDK and Tools. We're not actually going to look at the Software Development Kit directory today. Instead, we're going to go into Tools. So if you go into Tools, you'll see there's 2 folders, CP2102 Driver and Win32. Now, before you do anything, you'll need to go in and install a driver for your computer. Now, it really depends on what type of computer you have, but most of you will need the 64-bit driver, which is what I installed. However, if you have an older computer, maybe a Windows XP box that you're still using, you might want the 32-bit driver. And so the drivers are over here. Just install the one that you need, and then go back and open this Win32 directory. And you will see a number of different applications, the Ultra Simple, the Simple Grabber, and the Frame Grabber. The one that I think is the most impressive is the Frame Grabber. So I'm going to open up the Frame Grabber right now. And it'll ask me what COM port I'm going to use. It should default to the correct one, so I will say OK. And give it a moment, it'll open. You'll notice the motor stopped right now while it opened, because now it's being controlled. Okay, so this is the Frame Grabber. I've maximized it to full screen over here so you can see it. And in order to do this test, I want to introduce you to a friend of mine. This is kind of taking you into the background scenes of the DroneBot workshop filming process. And my friend is this guy over here. This is a little jig that I built actually a couple of years ago for doing filming, and you'll notice that this is about the same size that I am. The reason is I'm both the person in front of the camera and I'm the cameraman, and since I can't be at 2 places at once, in order to focus, I built this little device here, and it's got some focus targets on it, And, you know, it also has a white background to let me do a white balance. But I found out that when I was doing the scanning in this very small room, it actually is a pretty good target to demonstrate the RPI LIDAR with. So I'm going to use this device right now as a target. So at any rate, as I said, the room is very small, and remember, the minimum range of this device is 30 centimeters. So you're not going to get a great reading in this tiny room. This would work much better in a larger room, but nonetheless, you'll still get an idea of how this works. So I'm going to start the scan right now, and you start this by pressing this little button over here. And as you can see, we're getting some scan results right now. Now, let me show you something. I'm going to put my target over here. Now, can you see a straight line inside there? Let's move the straight line. Do you see that line moving over here? Let's move it over here. Move it there. That flat line that you're seeing is actually the surface over here on my target. Now there's another moving thing inside here as well, and if you'll watch, it's kind of like sitting at about the 240 degree mark right now, and it's moving down a little bit, and it's moving up a little bit. That, of course, is me. It's picking me up in there. And otherwise, you'll notice everything is confined mostly to the center, except for a few dots down around the 150 degree mark, and that actually represents a door opening that you can't see that's right behind you over here that goes outside of the workshop. So it's actually gone out there, and it's targeted on a couple of objects in the next room, which is, for your information, my laundry room. So it's probably hitting the dryer or something right now. So at any rate, it's a very impressive little display, and it also goes to show you the kind of data that you can get from a scanner like this, and that is the sort of data that a self-driving vehicle would be using in order to determine its position. So now that we've seen that, let's see if we can make some more use of our RPI LIDAR device. So for this experiment, we will need an Arduino Uno. Of course, we'll need our RPLIDAR device. We're also going to need a common anode RGB LED. Note that this is common anode and not the more popular common cathode variety. You'll also need 3 resistors. I used 150 ohm resistors, but pretty well any resistor in that range should suffice. Now let's go to the connections. We're going to connect things from the RPLIDAR to the Arduino first. So, on the connector for the RPLIDAR, starting on the top, we will connect the ground connection to the Arduino's ground. The RX, or receive connection on the RPLIDAR, will be connected to the transmit line on the Arduino, which is pin number 1. The TX, or transmit line, on the RPLIDAR is going to be connected to the Arduino's receive, which is pin number 0. The V5.0 connection on the RPLIDAR is the 5-volt power supply, and we will connect this to the 5-volt output from the Arduino. The next connection is a ground, and that will be connected to the existing ground connection. The Moto CTL connection is the motor control connection for the RPLIDAR. This will be connected to pin 3 of the Arduino so that we can send a pulse width modulated signal to control the motor speed. And finally, V-Moto. This is the power supply for the motor. Now you can connect this to an external 5-volt power supply if you wish. However, in this case, I'm going to use the Arduino's 5-volt supply. The RPLIDAR device has noise filtering on it to prevent some of that noise from getting into the data lines. However, again, you can use an external 5-volt supply if you'd prefer. Now we'll hook up the LED. The common anode of the LED is going to be connected to pin 12 of the Arduino. This allows us to enable and disable the LED. The red connection on the LED is connected through a 150 ohm resistor to pin 9 of the Arduino. The green connection goes through another 150 ohm dropping resistor, and it gets connected to pin 10. And finally, the blue connection is also passed through its dropping resistor and then connected to pin 11 on the Arduino. And so now that we've seen how to hook this up, let's take a look at a sketch that we'll be using in order to run our demonstration. Now, in order to use the RPLIDAR with the Arduino, you're going to need to grab some code for it and add a driver to your Arduino IDE. The RPLIDAR SDK is up on GitHub, and I've got the link for that in the article associated with this video, so go over there and take a look at it. Now, you can download this entire thing as a zip file, and I would recommend that you do that to take a look at the items that are inside it. However, that zip file cannot be installed directly into your Arduino IDE. It's just simply a matter of the fact that it's not structured correctly. I explain this in the article and show you how you can create your own zip file, and for your convenience I've created one as well, and you'll also find a link to that in the resources section of the article on the DronebotWorkshop.com website. So once you've got the zip file, go to your Arduino IDE because you'll need to install it. Go up to Sketch, go to Include Library, Add Zip Library. Select the folder that you downloaded your zip file to, in my case a downloads file, and then select the RPLIDAR driver, and then click OK to install it. I won't do that now because mine is already installed. Once you have it installed, there are two example programs that you can look at. Go into Examples and go to RPLIDAR driver, and you will see both Distance to Color and Simple Connect. Let's take a look at Simple Connect. Simple Connect is actually just a template that you can use in order to write your own code for the RPLIDAR device. And so in effect, it really doesn't do anything by itself. It just basically is a template that you'll be able to use to write other code. Now, if you do decide to run this in the Arduino IDE, it'll run fine, but the only thing that you will notice is that the LIDAR device will spin and nothing else will happen. But basically, you will start any code that you're using for this device by including the RPLIDAR library itself. And then after that, you'll create an instance of that driver that we're calling LIDAR. You'll also define the pin that you're using to control the motor speed. Now, we're using pin 3. You could use another pin, but it has to be one capable of pulse width modulation, because that's how you regulate the speed of the motor, which in turn regulates the scanning speed of the LIDAR itself. In this setup, you need to begin the LIDAR object. You use a begin, and you point it to serial, because our LIDAR device is connected to pins 0 and 1, which are the serial ports in an Arduino Uno. Now remember, these are the same places that the USB connection on the Arduino Uno is connected, so you actually can't use both at the same time. You're going to need to power your Uno with something other than your computer in order to make this work. So you'll upload your code to it and then disconnect it from the computer and power it with something else. The next thing we do in setup is simply set the RPLIDAR motor pin that we've defined, pin 3 in our case, as an output. And then we go into the loop, and this is basically the basics of reading data off the RPLIDAR device. We find out if the LIDAR is at a wait point. We say, is it okay? Is it at a wait point? If it is, we get the current point. We get data for every single point that we scan. And remember, we can bring in up to 8,000 of these points per second if we run this at full speed. Now, get current point can provide us the distance, the angle. There's also a Boolean that tells you whether this is the very first bit in a scan. So is this number 1 of the entire scan or not? And the quality of the signal is also set out as a byte value over here. Now, if we do get that data, we can perform our own data processing down here and use these variables within our processing. And indeed, when we write some proper code for this, that's exactly what we'll do. If it isn't at the wait point, then we stop the motor, we try to detect the LIDAR device, and if it is detected, we scan it. And then we start the motor all over again. And so that's the basics of using the LIDAR device. Now there's another example, and I'm not going to go through it in great detail because there's a lot to it there. There's more detail explained in the article if you're really interested, but I just want to show it to you. This is the distance to color example, and this is actually the one that you're going to load up to your Arduino IDE that we've wired up with the RGB LED. Now, the interesting thing about that RGB LED, as you recall, is that it's a common anode device, whereas the common cathode device is a bit more popular. The common anode device needs its common section connected to 5 volts. However, we've connected it to pin 12, as you'll see over here. So when we enable this pin, when we send it to 5 volts and bring it high, it provides the 5 volts through the common lead on the LED. This lets us actually completely turn the LED on and off through control of this pin. We define pins 9, 10, and 11 as the RGB pins. The rest of this is very similar. Again, we're defining the PWM connection to the motor as pin number 3. We have some functions which essentially convert color from angles. So we take the angles like display color, the float angle, the float distance, and we use this function and the previous one to create a unique color for that particular angle. And if you go through, you can actually read the parameters they've set for these over here. I'm not going to go through it now because it's just going to get a bit confusing. And in the setup, we'll go and we'll do the same thing. We'll begin serial, we'll bind it, we'll set the pins that we've defined as outputs. And this over here actually enables the LED but turns it off. Keep in mind, being a common anode LED, a 255 is actually fully off and a 0 is fully on. We define a couple of other variables, a couple of floats for the minimum distance and the angle at the minimum distance. And then in our loop, we do basically what you saw in the early example. If it's at a wait point, we perform the data processing, we get the angle and the distance and assign it to the LED. Otherwise, we go and we try to start the LIDAR device over and over again. So I know that's sort of a brief skim, not the normal detail I give you on the code, but you can take a look at the code and you'll essentially see what it's doing. So now that you've seen that, let's take a look at the code in action. So upload the distance to color sketch to your Arduino and we'll take a look at it. Alright, so I've got my RPLIDAR and Arduino and LED hooked up over here on the workbench. I've just got the RGB LED on this small solderless breadboard. That's also where I've connected the RPLIDAR connections. And one little hint, if you're trying to do this yourself, is how to make a connection to that connector. I didn't have that type of connector, but what I found is that this male header actually worked really good. What you do is you actually plug the connector onto the short ends over here, and then you can plug the long ends into your solderless breadboard. So that really worked out well and was making it quite easy in order to hook up the RPLIDAR. Now, you'll also notice that I've mounted the RPLIDAR up on a stand, and the reason is, if I keep it down on this level, on every scan it's going to actually start hitting the components on my Arduino and solderless breadboard, and we don't want that. Now, I'm hoping you're going to be able to see the RGB LED, because it actually is quite neat to watch this work, but I've had some difficulty filming RGB LEDs, so hopefully you will be able to see all the color changes that I am seeing, and if not, I apologize. Now, I'm driving everything off of a 9-volt battery. Remember, you can't use the USB port for this because the USB port transmit and receive shares the same pins as pins 1 and 2, and we're using that for the RPLIDAR. And using the library that we use right now, I couldn't find a way to switch over to software serial. So we kind of have to run this without being connected to the computer. So let's connect the 9-volt battery to it. And the LIDAR starts, and our light comes on. And as I move my target, which is just going to be my hand in this case, around the LIDAR device, hoping you can see that, I'm getting different colors on the LED. And as I come in closer and further from it, the colors tend to change. Remember, if I go too far out, it's going to trigger on the next nearest object it finds, which is probably one of the items on my workbench. I tried to clear the area as good as possible. But as I'm hoping you're seeing, the color goes through some quite dramatic changes depending on where the target is. And that's really great. It's obviously not that practical a use for the device, but it is showing the fact that it is capable of detecting the angle that the reflected object is at within the 360-degree perimeter. It's also detecting the distance that the thing is at, be it by the hue or the intensity of the LED. And of course this data could be used for a lot more practical purposes, including that in a self-driving car. So although it's a simple demonstration, this shows you how the RPLIDAR can be connected up to an Arduino. Alright, well that about wraps it up for today's video, but it most certainly does not wrap it up for these two sensors. These devices are just too amazing to just devote a small video to. So I'm going to be building a project with each of these devices. Now with the TF Mini LIDAR, what I have is a pan and tilt mechanism that I want to attach to it. I saw another YouTube project using another LIDAR device in which they did a 180-degree scan of a room, both horizontally and vertically, and created a really cool point cloud with it. And I think I could probably do the same thing with the TF Mini. So I'm working with that right now, and as soon as I have that working, I will release a video and article to show you how to do that. Now as for the RPLIDAR, that's an amazing device, and the obvious use for it would be in a self-driving vehicle. Now I have a robot car base, not the normal plastic one I use, but a really nice metal one from DF Robot that I actually purchased about 1.5 years ago and haven't put to use yet. I think it would be the perfect mate for this RPLIDAR device, and I'm going to start working with that. It may take a little while, but I intend to try to start working with a self-driving vehicle using the device. And of course, once I have something, I will release a video and article to show you how to do that. Now the best way to find out about these videos and their corresponding articles is to subscribe to the YouTube channel. So if you haven't done that already, please hit the subscribe button below. I would very much appreciate that. I would also appreciate it if you would sign up for the DroneBot Workshop newsletter. You'll find a link below the video as well as a form on the dronebotworkshop.com website. Now the newsletter is my way of keeping in touch with you to let you know what I'm working on in the workshop, but also to find out what it is you would like me to work on in the workshop and what articles and videos would be useful to you. So please subscribe to the newsletter and become part of that community. Until next time, please take care of yourselves, and I hope to see you again very soon here in the workshop. Goodbye for now.